Hi everyone. I forgot to record our lecture the other day for, I guess it was class 5, so I'm just going to quickly record what I missed and bring you up to date with that. So this was the slide that we are going to start with. We finished the previous class just doing an example problem. So we were looking at the integrated rate laws and how we can use these to solve questions where you're asked what the concentration might be after a given point in time. So I want to move to the concept of something called half-life, where half-life is the time required for a reaction to be basically 50% complete. It's the time required for the reactant concentration to drop to 50% of its initial amount. And it works out for first order reactions. Remember, first order reactions are ones with rate laws that look like rate equals K times concentration of A, where the sum of the exponents here is 1. This would be a first order reaction, and so what we find for a first order reaction is the half-life of the reaction is actually a constant. So what that means is when the reaction is half done, the time that takes, if you wait that same amount of time again, the reaction will cut again in half, another 50% drop. And then if you wait another half-life, it goes half again. So let's say you're starting at some initial concentration like you see right there. If you wait the amount of time required for the concentration to be cut in half, that would be this unit of time here, which is called the half-life, or T1 half. That half-life, if you wait that same amount of time again, you will get a concentration which is your initial over 4, which is half of what it was one half-life ago, A over 2. If you wait again, it'll be A over 8. If you wait it again, it'll be the initial concentration over 16. So half-life is very useful when we're talking about first order reactions for giving you a sense of how long it takes for the reaction to be half done. Because it is a constant, it doesn't matter what your initial concentration is. We know after a specific fixed amount of time, whatever that was, it'll be half that one half-life later. The same is not true though for second order or zero order or really any other order besides first order. So half-life is a less useful measure for other reaction orders, yet it's still something that we can look at. We're going to consider the integrated rate laws now for second order reactions of the type A plus A goes to product. So basically you have two A molecules coming together to give you a product, which would give you a rate law which looks like this, or another way is Ka squared. So the overall reaction is second order, bimolecular rate determining step. And yeah. So what we can do again is we can apply calculus to this situation just like we did for the first order rate laws in the previous class, and arrive at the following equation for a second order reaction. I just wanted to point out at this point that some books actually derive this slightly differently and have a 2 in front of the KT. If there's a 2 in front, and that's not meant to be superscript, that's just a 2 in there. If there's a 2 in there, then what that means is there's a sort of a different value of K that's used. While this is sometimes used, I would say it's not the normal convention. Most of the time, most sources use K values that are consistent with this equation for second order reactions. So you see a 2 there, just recognize that it can exist, but that's not what we're going to be using in this particular course. So what we get then is that 1 over the concentration of your starting material at some point in time is going to be equal to Kt plus 1 over your initial concentration that you began with. So graphically, if you plot the concentration of A versus time, visually, like first order and second order look kind of similar. Like there's obviously a difference if you see them side by side like you do here, but it can be often quite difficult with actual experimental data to look at that and say whether it's first order or second order. They're very easy to distinguish from zero order, which would be a straight line. But distinguishing first order and second order is quite difficult. However, we can graph them in different ways that makes them much easier. Okay, so one thing is if we, instead of plotting concentration of A versus time, we plot 1 over concentration of A versus time, what we see is we're going to be following this equation, which is y equals b, that's a constant, plus mx. And you see, this is the equation where that 2 is there, we're not supposed to have in here. So our k is going to be our slope, and t is going to be our variable, our independent variable, whereas that's going to be our dependent variable. So this is just a straight line, y equals mx plus b, and the slope will give you k, and plotting 1 over a versus time will give you a straight line equation if the reaction is second order, not if it's first order. We can express a half-life as well for a second order reaction. All we do is we take t1 half as our time and insert that into our integrated rate law, and then we take concentration of A at time t is equal to 1/2 your original concentration, so this would be half of what the concentration was that you started with. Put that in there and solve, and what we get is an equation for half-life where the half-life is equal to 1 over k times the initial concentration of A naught. Now, unlike the case for first order reactions, this one is maybe a little bit less useful because, as you can see, the half-life is not a constant. The half-life depends on what starting concentration you're at. So if you change the starting concentration, you change the half-life. Such as it is. You know, that's just the nature of the beast. Just makes this a little bit less useful because half-life is no longer a constant like it is for a first order reaction. All right, we have a question here, and it says, what is the half-life for a second order decomposition? The half-life for a second order decomposition of HI is 15.4 seconds. So T1 half is 15.4 seconds. When the initial concentration of HI, so that means our initial concentration of HI is 0.67 molar. What is the rate constant for the reaction? Well, this isn't actually too bad. If you look at our equation for our half-life from our previous slide, T1 half equals 1 over k times our initial concentration of A, and we can rearrange this to say k equals 1 over T1 half times A naught. And that equals 1 over 15.4 seconds times our concentration, which is 0.67 molar. And I have this solved somewhere. I have just 1 second. Yeah, sorry about that. Yeah, this works out to become 0.097 to the correct number of sig figs. And you can see that the units there are going to be molarity to the -1, seconds to the -1, which right out of the gate, if you look at those units, you could tell that this is a second order rate constant. First order rate constants are always in units of time, -1. And second order is always molarity to the -1, time to the -1, just for future reference. Second order reactions of a different type, where you have A plus B goes to product, gives you a rate law that looks like this. Again, this is an elementary reaction. You can do integrated rate laws for these. They are far more complex, and we won't be handling those in this course. We're only doing the A plus A type, the more kind of dimerization types. But it's doable. You can do this for other ones. It's just a little bit more complex. So we're going to keep it simple at this point. Next, we're going to move to zero order reactions, and it's actually impossible to have a zero order elementary reaction because an elementary reaction involves some number of molecules reacting together in one step. A zero order reaction would imply there's nothing reacting. However, you can have zero order reactions for complex reactions. And for complex reactions, a zero order reaction is one where just the rate equals a constant. The rate doesn't speed up or slow down depending on what point in the reaction you're at, which is actually quite interesting. I sometimes think of a zero order reaction as a little bit like a ticket booth back when you didn't buy tickets online, but you had to go to a place and purchase tickets. You can see there's a little ticket booth, the windows here, and you place your order, and there's only a certain rate at which this ticket booth can handle customers, sell tickets, and deal them out. And if the line had 5 people in the line or 5,000 people in the line, it doesn't make any difference. The rate at which they can sell tickets is the same regardless of the number of people lined up. So this is like a chemical reaction where, let's say the ticket booth is something like an enzyme, and the enzyme is doing a chemical reaction on substrates, which are all the people in the line here. It doesn't matter what the concentration is of the reactant, of the substrate. What matters is how quickly the enzyme can work. And you can't speed that up or slow it down by adding more or less reagent. So many biological reactions have zero order kinetics. They occur at a very specific pace regardless of the concentration of the substrate that's reacting. Great example of this is metabolism of alcohol in the body. We have enzymes that do this, liver alcohol dehydrogenase, for example. And what happens if you have alcohol in your bloodstream? You have a blood alcohol concentration, which is measured with a breathalyzer. Your body can process that alcohol at a very specific fixed rate. So if you were to have a lot of alcohol in your system or a little bit of alcohol, doesn't matter. Your enzymes will work at a fixed pace to remove the alcohol from your bloodstream. So obviously if you have a lot of alcohol in there, it just means it's going to take a lot longer. Here's a question. A 170-pound individual consumed several Jaeger bombs, after which his blood alcohol level was 0.155%, which means 1.55 grams of ethanol per liter of blood. Assuming that alcohol metabolism is zero order, like many biological reactions, and that K equals 0.030% per hour, how long must he wait till he can legally drive? Legal limit in Nova Scotia, I believe, is 0.08. Not that you want to have it timed right down to the percent. You probably want to, play it safe on this type of thing. Nevertheless, our equation is going to be our concentration of A at time t is going to be equal to whatever our initial concentration was, subtract K times T. Okay, so you start at some value, and then it's going to be removed at a very specific rate, which is K, and then however long you have is T. And so that means in this example, our initial concentration, which we're going to express in percentage, no reason we can't do that, multiplied by K, 0.030% per hour, multiplied by the number of hours, and the legal limit that we're trying to get to is 0.080%. So this is in T right over here. Bit of a mess there. So yeah, let's rewrite that a little bit. 0.080% equals 0.155% minus 0.030% per hour times T. That's gone. Okay, so what we can do is subtract 0.155 from each side, and what that will give us is negative 0.075 equals negative 0.030% per hour times t. T equals 0.075% divided by 0.030% per hour equals 2.5 hours. There we go. So what this tells us is that after 2.5 hours, assuming this is our value of k, that value is going to be specific to each individual. Everyone has their own value of k. 2.5 hours from that point, your blood alcohol level should be down to the current legal limit in Nova Scotia. Doesn't mean you should drive. I'd wait a little longer than that if it was me. The integrated rate laws, remember this is a plot showing our concentration of A versus time down at the bottom. It's a straight line. This equation is a straight line. Y equals B plus mx, where m is the slope, which is minus k. And you can see the half-life depends quite a bit on where you start. For it to go from point 2 to point 1 would be the half-life if you're starting at point 2, but to go from point 1 to 0.05 would take only half that time. So again, the half-life is not as useful here because it does depend on what our initial concentration is. Nevertheless, we can still express it that way. So here we have a summary of our integrated rate equations. And remember that we're not using the version for the second order with the 2 in it, just to know that those exist, but we're not going to be using those. We're just cross the 2 out. We're going to be using the k values using the more conventional form. We'd like to examine for a minute what impact temperature has on the rate of chemical reactions. And one thing that we know experimentally is that raising the temperature of a reaction will cause the rate of the reaction to increase. So that's important. What we find is that it increases in an exponential fashion. So as you can see here, we're looking at the rate constant k for a given chemical reaction versus temperature, and it's not a straight line, right? It curves upwards like an exponential function. And a chemist by the name of Arrhenius many years ago applied math to this. What he wanted to do was express what this mathematical function might look like, and he did this empirically, which is to say he ran a bunch of experiments and measured rate constant versus temperature, fitted the data, and then found a mathematical equation that fit that data that he was getting. The opposite, I guess, of empirically determining an equation would be to determine it from first principles, which sometimes we call ab initio, which basically means take fundamental principles and figure out what an equation for a certain relationship must be. That's not what was done here with the Arrhenius equation. It was done empirically. And this was the result of his efforts. He found that the rate constant k was related to temperature according to this equation, which is k equals a, which is a constant, sometimes we call it the pre-exponential factor, times e to the minus ea over RT. And what EA is something called the activation energy. It's the energy that's required when there's a collision. It's the amount of energy that needs to be present in the reacting species in order for the reaction to proceed to give you products. We'll look at that in more detail in the future. R is just the gas constant. It's equal to 8.314 joules per k-mole. And so we have, that's a constant. EA is a constant for a given reaction. A is a constant, so our only variables here are K and T. And because T is in the denominator of a negative exponent, this is an exponential increase as T goes up. If you, we can do what we call linearize this equation. If we take the natural log of both sides, what happens is it transforms into this form where we have natural log of k equals natural log of a minus EA over R times 1 over T. This is again in a straight line equation because ln k is our dependent variable. Ln a is a constant. Minus EA over R becomes our slope for this equation, or gradient for this equation. EA is a constant, and so is R. And then 1 over T would be our independent variable, X. So this is just another form of the exact same equation, which you might find useful. I just wanted to let you know that I have done this myself experimentally before. This is a paper I published back over 10 years ago now, where in our lab we were able to make this particular compound, which is a fairly reactive molecule for reasons that maybe you'll learn in organic in the future. It's called an anti-aromatic compound. And what we have is a carbon atom with 3 bonds and a positive charge, which is also making this pretty reactive. But using ultra-fast spectroscopy, I guess it's not ultra-fast, it's just very fast. It happens on the order of nanoseconds. We're able to record a spectrum of this particular species, which is this line here. And this absorbance spectrum is just showing what wavelengths of light the compound absorbs. And this was generated 0.6 microseconds. This spectrum was recorded 0.6 microseconds after the compound was generated. Then what we did is waited a short period of time to 3.4 microseconds, which again is a very short period of time. And what we see is essentially the same absorbance, same graph. It's just shrunk a little bit. And it's shrunk because some of this compound has decomposed, it's gone away. And then if you wait a little longer, you see the same thing again. What we're watching here is this cation reacting, undergoing reaction. I think it's a first order reaction in this case. And using this technique, we're able to measure K. And if you do it at different temperatures and then you plot ln K versus 1 over T, you get a straight line like we saw in the previous slide, and you can get the activation energy from the fact that the slope is equal to minus EA over R, like we saw in the previous slide. So this is useful. It's a method for measuring activation energies for different reactions, and we're going to be looking in the future at how we understand activation energy to be when we're looking at what's called reaction profiles. So this is just another form of the Arrhenius equation, and this is a very useful form of the equation when we are considering a reaction that we might want to do at 2 different temperatures. What this is saying is that the natural log of the rate constant 2 over rate constant 1, so what this is saying is the rate constant at 1 temperature versus the rate constant at a 2nd temperature is equal to minus EA over R times 1 over T2 minus 1 over T1. This is the identical equation, it's just slightly rearranged if you prefer to have your right-hand side positive rather than negative. Doesn't matter which one you use, just make sure you use one of them and you don't mix and match parts of these 2 equations. This is super useful if you happen to know the activation energy for a reaction and you know the rate constant at 1 temperature. Using this equation, you can then predict what the rate constant will be at any other temperature that we have to deal with. And this would be extremely useful. Imagine you are working in industry, and let's say you have a chemical reaction that takes 3 weeks, and you need to get that reaction down to 2 days. Well, you can calculate at what temperature you would need to speed that reaction up enough to make it over in 2 days. So this is quite a powerful form of this equation. Very, very useful. Let's make use of it. It says the reaction is found to have an activation energy equal to 108 kilojoules per mole if the rate constant for the reaction, call that K1, is 4.60 times 10 to the minus 6 seconds to the minus 1. At T1, at 275 degrees Kelvin, what will the rate constant be at T2, which is 366 degrees Kelvin? We don't know, but we can find out. we know what we're doing here. One thing I want to point out, we can tell right away what the order of this reaction is, believe it or not, because we see the units here for the rate constant. So we know because this is seconds to the minus 1, this has got to be a first order reaction. All right, so our equation that we're going to be using is the natural log. You can see it on the previous slide. Why don't we use the one on the left? We have K2 over K1 equals minus EA, you can see that over R, 1 over T2 minus 1 over T1. What we want to do is rearrange this so we're creating an expression in terms of K2. So if we raise each side to the power of E, so E to the power of each side, E to the natural log of K2 over K1 is just K2 over K1. E minus EA over R, 1 over T2 minus 1 over T1. And now we just multiply each side by K1. That gives us K2 equals, and these are lowercase k's, next, all we need to do is plug in the numbers that we have from above. That equals 4.60 times 10 to the minus 6 seconds to the minus 1 times E. Now, our units for EA have to match with our units for R, and because R is 8.314 joules per mole K, we need our EA to also be in joules, but it's in kilojoules here, so we just multiply joules per mole. And you see the joules per mole goes with joules per mole, and we're left with 1 over K on the bottom, times 1 over T2 minus 1 over 5K. And if we do this out, the number that we should arrive at is 0.58 seconds to the minus 1. And as you can see, that this is a far larger value than what we had at the cooler temperature, 10 to the minus 6. You know, it's like 10,000 times bigger, or 100,000 times bigger. And so for this reason, this reaction is going to be a lot faster at the higher temperature, which is what we always see. Great, so that's it. That's the end of what we're going to be covering in today's lecture. We pick up from here next class in class 6. Thank you, everybody.